Welcome to this talk about Docker and databases. My name is Joakim. I work at Uber in our storage platform team. And so during this conference, there's been a lot of talk about Kubernetes and that Docker is not really a thing. It's just a tool in a bigger box. That is indeed true. But at Uber, we don't use Kubernetes. We build a lot of stuff ourselves. So like this small animation, you will probably hear things today where you think, I wouldn't do that if it was me. This is pretty strange. So that's kind of part of the entertainment today. Demanding, and I do that. I've been at Uber for 3.5 years by now. I'm located in Denmark, where we have a small infrastructure office, about 50, 60 people. Our platform team in general builds online storage, so that means like normal transactional databases, key value stores, stuff like that. Separately, there's data warehousing and analytics and all that stuff. We don't do that. There's a whole separate team doing all of that. But in general, we are in Aarhus, Denmark, Vilnius in Lithuania, and then Bay Area. Okay, a bit of background. As I said, Uber is a somewhat special case, which is why you shouldn't just take everything I say at face value. When I joined Uber about 4 years ago, Uber was very much a bare metal kind of place. Everything was managed through Puppet. If you wanted to deploy a new service, you would do some kind of Puppet rollout. Then at some point, we started migrating to Docker, so we have our own deployment platform that can deploy Docker containers. And after a while, we also thought, well, maybe we should move to a more standard place. And we decided to move to Mesos and Aurora. Of course, more things are happening since then, but actually this migration is still happening because it's just a big, big place. And mainly because we have so many services. So Uber has, I think everybody lost count by now, but more than 2,000 microservices that kind of make up the entire Uber system. So Uber, when you look at the app, I assume most people kind of know the app. It's pretty simple. You can just order a car and that's it. How hard can it be? But it actually turns out it's pretty hard. So we have around 2,000, maybe even 3,000 microservices by now. We have more than 3,000 engineers. And all the engineering efforts are basically DevOps efforts. So all engineers are responsible for developing their own services, deploying their own services, monitoring their own services, fixing bugs. All that stuff is completely decentralized. That, of course, means that if we want to migrate somewhere, like at a global level, that becomes very hard and takes a long time. And then we have this let build as build thing, or we used to have it at least, which basically meant that if you need something, you just go ahead and build it. Don't wait for anybody else. If somebody is slowing you down, you just do it. That, of course, also leads to a proliferation of microservices. And the background picture, you might think this is just some random picture I found off the internet. It is actually not. This is an actual picture of the service dependencies. It's not the full picture. It is the picture of service dependencies from our running services based on real traffic, like live traffic coming in through the system. To me, that is, it seems pretty scary when you look at it. And I guess it kind of is. Okay. So in all this, we run storage. And we mainly run 4 storage solutions: MySQL, Cassandra, ElasticSearch, and Redis. Like, is Redis a storage solution? Well, maybe it is, maybe it isn't, but we just say it is. MySQL is our primary storage. Uber has a storage system called schemaless, which is basically a sharded database solution on top of MySQL. So we run around roughly 20,000 MySQL databases, 4,000 Cassandra nodes, 4,000 ElasticSearch nodes, and around 150,000 Redis nodes. You might think that's a big number, and it kind of is. But for Redis is a bit of a special case because we run a trend proxy Redis, which is basically a sharded Redis. And it has a default setup where you get 40 shards per cluster. And they are way, way overcommitted. So these 150 Redis nodes run on something like 300 physical hosts. So it's not as bad as it sounds. In total, we manage a lot of storage, petabytes and petabytes of data. And particularly MySQL and schemaless is special because it's an append-only store. So we basically never delete anything. When I say never, we of course do, because now there are compliance things coming in. But it was built as an append-only store. And that means that every time you take a trip, we store the trip and the details about the trip forever. And then, of course, compliance. Yeah, so storage has this peculiar problem, interesting thing that if our trip growth goes up, like more load comes into the servers, but we don't really get rid of any data, so we have to store more and more and more and more data all the time. Okay. So that's interesting in itself. But of course, this talk is more about Docker. And I don't think I've been to a single talk here where databases were mentioned as a thing to put inside Docker. And you might also think that's pretty weird. It goes against all common wisdom. So why would we do that? And then there are actually a couple of reasons why it makes sense. It might not make sense in all cases. But for us, it's really about increased flexibility, unification of how do our hosts look? Do we have different host classes? Do we have different puppet roles? Do we have different installation policies and whatnot? It's also a matter of how do we utilize our hosts? Because we have a lot of databases, and we have a lot of teams. They all need, or most of them need some kind of storage. And if we just allocate physical hosts to all teams, then we have a lot of wasted hardware. And then there's a question of automation. Because we really want to, even though that we have thousands and thousands of databases, we don't want to have an increased scale in human power too. So we need to automate. And Docker is really a component in all this. But as you will see, Docker also plays a fairly small role in the overall architecture. So what we're building is a single management platform that can manage all of our storage. So that means that no matter if you're doing MySQL or ElasticSearch or Cassandra or something else, you can go to the same system. You can provision things, you can monitor it, you can add capacity, you can remove it, you can do whatever you need. And we can have a single on-call rotation that covers all of our storage solutions. And they don't have to have intricate knowledge of deployment and error handling and all that stuff that you usually have to. We call this management platform Odin for various reasons. And this is basically the system that I work on a daily basis. Let's start out with looking at what we actually can do. And this is not something that you can use. This is not open source. It's not available for anybody. But it might serve as inspiration. One thing that we realized was that even though we are doing deep level infrastructure, having a good UI to visualize is a really good thing. So Unfortunately, I cannot show you the live system because there's a little bit of smudging going on and some numbers that I don't really want to reveal. In general, I can talk a lot about technical stuff about Uber, but I cannot really talk about business metrics. So there's a couple of things that I cannot show you in the live system. So I have screenshots from the live system. So go into the Odin UI, you can pick which technology you want, and you can actually see there are more technologies than I had before. That's because you can actually plug into the system as you want. But you can see Cassandra and ElasticSearch and Redis and schemaless. Then we have some called SoADB MySQL, which is just like raw MySQL. And we also have some Postgres, we also have Vertica, and we also have some blob storage. Okay, so you can go into the schemaless section, and here you can see who's on call. You can see who's doing what right now, so we have all these active workflows. Those are basically things that people are doing right now. So they might be expanding capacity, they might be replacing nodes, any kind of maintenance. And you can dig into like which instances do we have, which versions are they running, and you can also get a list of all the things that are currently wrong in the schemaless part of the system. So we use this UI whenever you're on call to kind of inspect like what is going on. If you got an alert, you can go in to see like what is the state of the system. And you could go into what we call an instance. That's basically, if you're a team, you probably get an instance of schemaless or MySQL or Cassandra. And you can see like, versioning information, again, issues. This ad hoc store is, as the name indicates, a test store. You can see if anybody's doing maintenance on it, you can see that. You can create a new data store if you wanted. You can see all data stores in there, and you can see the sizes of them. You can also see who owns this thing. You can go into a specific cluster, and you can see the size of the cluster. You can again see all the things that are wrong with this particular cluster. You can see the cluster topology. So you can see some nodes are actually connected to the cluster, some are just sitting there. They might just be sitting there for different reasons. And for each node, you can see like how much disk space do they take up, and the host that they are running on. You can go into a single node and see status about that. So you can kind of go back and forth, drill into a cluster and into a node and back again. Here you can also see that a single node actually consists of multiple containers. We'll get back to that later on. But in this case, it's a schemaless node, and a schemaless node actually has a MySQL container. It also has a Raft replication container. We don't use normal MySQL replication, we use Raft replication, so there's another container for that. And there's a backup container, there's a logging container, there's all sorts of stuff. So we really try to go for like micro containers that we can upgrade individually. So that one of the big differences between running stateless services and stateful services is that you don't really want to upgrade your database that often. Or you don't want to restart the process that often because it will lose its cache, it needs to reload all sorts of data. So splitting the functionality into separate containers means that we can give them separate life cycles. And finally, you can go into a host and see what is currently running on the host, which type of host is it, how much disk space does it have. And here you can already see that we actually run not a single database on our host, but we run multiple databases on our hosts, which is one of those things that traditionally you don't do, but we do it for a couple of reasons. One reason is the efficiency of doing backups and restores. So if you have one node, let's say you have let's see, what is this? No, it doesn't. This is probably an 8 terabyte host. If you have a single database that is completely full on a host and it goes down, you need to restore somewhere else. Now you need to transfer 8 terabytes somewhere else. Now in this case, we have like 7 databases running on the host. So if the host goes down, we need to transfer 7 databases somewhere else, but we can do that in parallel onto 7 new hosts. That means that we can back up and restore much faster. And we can recover much faster, and the blast radius of a single error, of a single fault, is also smaller. Okay. Another key part of the system is that you can actually inspect all the things that are currently wrong in the system. And by wrong, I mean things that are kind of off. Typically, you have a system and you want the system to be in a specific state, but typically that state has drifted somehow. So that might be that somebody logged into a host and changed something, somebody installed a new kernel version, a disk died, a CPU died, a memory bank died. Like all sorts of stuff might be wrong. That might or might not actually trigger an alert, and you might or might not want to have an alert. But somewhere, it is just extremely nice to be able to see all the things that are wrong, and then act on it, maybe at a later stage. So we call these issues. So issues are all the things that are wrong in our system. And we actually have a lot of issues, because there's always something wrong. And it might be stuff like the host is dead, but it might also be that a cluster is over-provisioned or under-provisioned, or that a host is disabled while it should be enabled, or is enabled while it should be disabled. Stuff like that. So you can inspect all that through this UI also. And you can invoke operations if you want to do something, like let's say you want to add a slave to a MySQL cluster. You invoke what we call a workflow that will go through a process of doing that and will only terminate once it has successfully been added. And then finally, for the UI part here, all this UI is actually built on top of an underlying information graph database. Because one thing is having a UI, that's all nice and dandy, but if you want to build custom tooling or build ad hoc tooling, like in this particular case, let's say you want to find all the hosts that have a specific kernel version, 4.38 for example, that have databases running that are owned by a specific team. Okay, so that's probably not something that we have in the UI, but you can write this graph query and find the information. And this graph information actually contains all our infrastructure, so all our hosts, all our databases, all our ownership, everything that we could possibly want in order to operate the system. And you can write these ad hoc graph queries to extract data from it. And all our UI is actually based on this. Okay. So that's all nice, but so the question is, how do we actually do this? So the first attempt is, of course, just to add more people to the problem. For our team, that's not really something we can do. So we need to automate. And the first part of automation is really going from a pets to a kettle kind of view. I'm sure most of you have been in a place, or maybe you are in a place, where you know all your servers, you know what they're doing. If they go down, you know exactly what to do about it. You will also try to nurse them back into life. But if you really want to scale, you need to go into a place where they're all just the same. And a single failure, or even multiple failures, isn't really a problem because you just replace them. Of course, when we're talking about servers and hardware, there's also a cost, like cattle. So cattle you also don't kill off just as soon as they get sick. You try to kind of make them good again. But in the bigger picture, you really want to not care about the individual servers, but care about the overall picture. Another way of thinking about it is really you want to get away from the procedural way of doing things, where you have like scripts. So this animation down here is an example of how we used to do operations before we built all this infrastructure, which is really just you have to do a lot of steps. You read runbooks. Runbooks are insanely long and complicated. You need SSH and direct access to hosts. It's error-prone. It's time-consuming. And if it fails, nobody really knows then what. So the state we want to go to, we call that goal state. You might also call it configuration-driven. It's a place where everything is automated. It states what you want to do, not how you want to do it. It's disconnected at opponent, so that means that once you have said, I want the world to look like this, you just disconnect and go back to sleep. And what you actually do is you don't go into a database or into a host and do a change. You change some configuration, and that gets applied. And typically, the configuration is global configuration. It means that eventually there's no operator needed to actually do this. And for this to work, you also have to have a system that continuously monitors and gets the state of the system. Okay. Oops. So we have this operational model that we work off, where we basically say we have our goal state. Our goal state is basically a definition of what databases do we want, the cluster topologies, the sizes, who owns what. We apply that state into actual live production. I get into the details about how we do that. We then inspect that state. And we generate these issues that are things that are kind of not where we want them to be. And we analyze the issues, and we take an action. And the action is changing the goal state, and now we have this perpetual cycle. And all the while we do that, we also collect all the information into this global view, so that we can build a UI, we can build ad hoc tooling, and we can build all sorts of stuff on top of it. Slightly more concretely, this is implemented by a couple of systems. All our goal state is basically a Git config. So at Uber we have basically a Git as a service, where you can do push and pull and do patches and stuff like that as a service. So we apply this Git configuration onto workers that are running on hosts. So for every single, so we call it node. A node is actually a database process, not a host. So we have hosts that have multiple nodes inside it. So we take this configuration, let some workers apply it, and we expect for drift, find issues, drop the issues into a system called Grail. Grail is this underlying infrastructure graph database that we also built. And we analyze it. So that's how we get auto-remediation, is by having issues collected automatically, analyzed automatically, and then fixed also automatically. Okay, just a small example of how could like a goal state configuration look. It's quite simple. Basically, all the configuration is stored in Git in YAML files. The YAML files basically define instances, clusters, nodes, how they're related. Everything you need to start a process and manage it. And you can actually just clone a Git repository and start editing these files and adding clusters and whatnot. And once you commit it, those clusters will just be launched completely automated. Typically, you don't edit them by hand because doing that is kind of dangerous and error prone. And again, we kind of want to get the humans out of the picture. So we have various endpoints for modifying. Like if you want to add a new cluster, there's an add cluster endpoint that will kind of do the right configuration change. Okay. So the way that we actually get nodes up and running is by having all the various storage engines will contribute their configuration into this shared system that we call Odin. Odin will schedule tasks against a scheduler. The scheduler is actually an abstract thing. It can be Mesas, it can be our own custom scheduler. It could theoretically also be Kubernetes. The scheduler will have a placement engine. For stateful services, it turns out that particularly when you just start co-locating, you need quite intelligent placement. Because you want anti-affinity, you don't want to have multiple clusters from the same, or multiple nodes from the same cluster on the same host. You want to diversify across racks. You want to make sure there's enough room on the disk. You also want to make sure there's enough room for you to actually grow at the pace that you're currently growing. So placement is actually also a fairly complicated effort. Anyway, the schedule will then launch our node workers on hosts. And the node workers will start up a goal state engine that will fetch goal state from the global system, Odin, evaluate it, check what is the current state of the system, If something needs to be done, apply it, and then read off the new states and send that back. And this happens in a 10-second interval. So this happens all the time. You can also think of this somewhat like Puppet or something like that. We'll also kind of try to go to a specific state. The main difference here is that we also collect actual states, and we do it much more frequently. So the reaction time from an outside event is around 10 seconds. So what is it that we react to? Well, so we react to, like, if you want to define a new database, it will be spawned here. If you want to shut it down, that will be handled here. If you want to, in like pure MySQL land, want to do a master promotion, also handled in here. So these these goal state engines are completely idempotent, so they will just execute this again and again and again by themselves. So there's no coordination involved. And the good thing is that they're really robust. Of course, that takes some engineering effort, but they will just keep on trucking. And they will even do that even if the upstream system is down. So let's say that our global system is gone, and you go in and you kill off a database. Well, that database will come into life by itself. If you do a fleet-wide reboot by accident, then the whole thing will pop up by itself, because these goal state engines will run no matter what happens. Okay, so that's the application part. For the fixing part, we have these issues, as I mentioned. We have rules and we have workflows. Basically, we take all the issues, we wrangle them into a rules engine, and outcomes a number of actions. And actions can then either be triggered automatically or by an operator. So doing things automatically is kind of dangerous, because you can get into all sorts of feedback loops where you add something and then another thing will remove it again, or while you're adding something, it will be removed because it's not healthy. All sorts of strange stuff can happen. So we're quite pessimistic about doing it fully automatic, but the exact same mechanism can be used for an operator triggered. So if you go into the UI, you will actually see we have all these issues, and these ones you can fix. You just click a button, and then it will fix itself, or it will at least attempt to fix it. And then we have a workflow engine that will actually do the fix. And as I said, fixing is really about changing the goal state. Now we have a workflow engine that is also custom and in-house built. But I guess if you think about it, it's kind of serverless, because you can upload a workflow to it. And the workflow is basically just an invocation of a series of endpoints, and all the endpoints you can do like a serverless thing if you want that. The important part about the workflow engine that we have is that it guarantees the execution of a workflow. So you upload a workflow, which is basically just a DSL indicating I want to do like different steps, and it will make sure that this request has succeeded before it continues. And if it doesn't succeed, it will just retry it. So retry is built in. So many of our workflows are really structured in a way that we do a change in Git, and then we wait for the change to take effect, which is really nice, because I'm sure you have all tried. You do make a change somewhere, and now you need to wait for it to kind of be ready. So you go into a different system, and you take some log files, you take some status, you take something else. The way we structure is really you execute the action and you wait for the result to be visible in the system. And then you're done. Okay, so that's a lot of stuff about like how we, like on a generic level, operate our system. So what about Docker itself? Well, Docker does play a small but quite important role, because, well, all our processes run in Docker images. So we can have since everything runs inside Docker, very little runs outside Docker. That means that we can have a single host image for all our storage engines, for all our storage hosts, and indeed all our hosts globally. We can also have multiple different versions of storage engines on the same host. Like if you don't use Docker and you just use MySQL, for example, running different versions of MySQL on a host, well, it's possible, but it's kind of a pain, especially if you need different versions of libc or whatever. That just becomes immensely painful. And of course, you get the unified build system, and better portability across environments. So if I want to test something locally, I can emulate the same setup as we have in production. And then, of course, we can co-locate multiple nodes on the same hosts, which, of course, you can do without Docker. It's just much easier if you have it. So a couple of details about how we actually use Docker. So we just use pure like Docker engine. We are still at 1.12.6, I believe. Upgrading Docker is a pain. I don't know how many of you know have tried running Docker large scale. Not a lot of people actually have that. I think we have in total 450,000 Docker containers running in production right now, like ballpark number. So that means that if Docker starts acting up, we will be hit by it on a lot of nodes. Okay. So we use Docker engine, nothing else. Docker is configured with overlay FS, overlay 2 by now, just for the container itself, but we use host volumes for all the data, of course, because we don't want the data inside the containers. All the data is sitting on host volumes on SSD drives with RAID 0, a bit more detail about that. Of course, live restarting. We use host networking. It turns out also that the bridge networking, which is kind of the default thing in Docker, is kind of buggy. You get all sorts of weirdo connection errors if you use it, again, large scale. Typically, you don't notice it, but when you use it large scale, you will see all sorts of weirdo network errors pop up. Then we have the isolation parts. As I said, one storage node consists of multiple containers. So we use like a nested container thing, like a little bit like Kubernetes pods. I'll get back to that also. And for logging, we just use station logging from Docker. We add node names as labels, and we take file people, pick them up, drop them into Kafka, goes into ELK. So a fairly standard setup, I would say. A bit of details about our disk layout and volumes. Our vast majority of current hosts are running this setup where we just have typically 4, 5, 8 SSD drives per host. They are running software RAID 0 with x84 on top of it. And then we just run Docker containers straight on top of that. Now, that kind of works nicely because the containers can grow as they want. But it doesn't give a whole lot of I/O isolation. So if you have noisy neighbors, that's going to be a problem. We have been in the fortunate situation that the usage patterns for our storage engines means that we don't have a lot of noisy neighbors. So we've been able to pull this off for quite a while. We are moving to a place where instead of just one shared volume, we will run hardware RAID 0 with LVM on top of it, and we will, per container, we will allocate an LVM volume and apply I/O throttling for each volume, so that we can prevent any single container from taking down the entire system. Now that is, of course, slightly less flexible because now you have a pre-allocated volume size per node, but that's kind of you cannot, unfortunately, win it all. Oh, you might say that, why don't you use CFQ scheduling if anybody's into that? CFQ scheduling is the kernel scheduler that can be used to do per C-group I/O limiting. But CFQ scheduling is quite expensive in terms of latency and throughput. We have actually seen cases where our performance goes down by 10x if we enable CFQ scheduling on the kernel. So that's not really good for storage. Okay. For nested containers, as I said, it looks like Kubernetes pods, but then isn't quite. So any storage node will have multiple containers. Because there will be at least a worker process that will manage the actual database process. They all run inside the same C group, so they're limited, but they share the resources. But the important part here is that each container has its own lifecycle and its own versioning. So that means that we can upgrade the worker part of the node without taking down the database process, or we can upgrade the database process, or we can upgrade any kind of node, any kind of container inside that pod without taking the other containers down. So we have one basic principle, and that is we keep the containers alive at all costs, because it is stateful. And this is one of the big differences between stateful and stateless. Even though you have a system on top that might or might not be able to handle failures, we keep these containers alive forever until we actively shut them down. So even though a configuration goes away, we'll keep the container alive. Even though you actually unschedule the container, it will, at least we'll keep the files around. If you upgrade anything, they will be kept alive. So yeah, the databases will never go away until you explicitly tell it to. And that is different from typically how Kubernetes pods works or Mesos nested containers. And this is one of the reasons why we're also building our own things. Not necessarily that we don't want to use stuff like Kubernetes, but stateful services in like a containerized world is new. So we're also kind of seeing what makes sense to do. And once that's been figured out, we can always kind of put it back into a standard system. Okay. Now, I don't know how many of you have used Docker at large scale. Docker is like immensely painful to operate at scale. Indeed, I think many people are going away from Docker Engine, just using pure runc. We are also moving in that direction. That's just because Docker kind of sucks. I don't know if there's any Docker contributors or people in here. Hope I don't offend you by this. But it is a fact that every single time we upgrade Docker, there are new issues popping up that you think, how can this possibly happen? So we just a month ago, we upgraded from Docker 1.12.2 to 1.12.6, which I think is a pretty small upgrade, should just work. No, it doesn't just work. Sometimes Docker daemon just won't start, or it's hanging, or weird stuff all over the place. So things we have encountered, as I mentioned, bridge networking issues, general stability issues, storage drivers are in flux. Now we are on overlay 2, but like when we started overlay, it didn't exist. So we had device mapper instead. That also had a lot of bugs. An interesting fact is that if you use Docker logging, if the Docker daemon is blocked for whatever reason, your logging will also be blocked because standard out cannot, if you're logging to standard out, that is, standard out cannot kind of go anywhere, and then the whole process might actually block, because typically you don't use an async logger for your standard out stuff, but you really should. So that might actually stop your entire process. We've seen this where MySQL just stops working because it wants to log something, but it cannot. That's kind of annoying. So there's a lot of different things for Docker. Okay. So as I said, should you, or should we even be doing any of this? Because it is kind of, there's a lot of stuff to do, and there's a lot of stuff that we have done. It's kind of fun. That's one of the fun reasons to work at Uber, and I don't want to advertise too much, but one of the fun things about working at Uber is that we get to do all of this stuff that quite few people actually get to do. Most likely you shouldn't. You should use something like Kubernetes, Kubler, or whatever, some kind of integrated solution that will kind of fit into probably a smaller scale. Because all the things that we had to build actually took quite a long time. So just our storage engine team is 75 people. Our infrastructure team is 300, closer to 400 people. And we kind of have the resources to build all this. Previous companies I've been at, it's like, there's no infrastructure team. It's just engineering or DevOps. There's engineering that will then be rebranded into DevOps. Now you do all the stuff, but you have to build features for end users. You have to manage your servers. You have to build infrastructure. So building like an advanced placement engine or just simple log aggregation can be hard enough. So if you have to build all of this, that's quite an investment. But the things that we have built, so these are links, I believe the slides will be shared. So these are links to a couple of blog posts that we have. Grail, this infrastructure, information, aggregation, graph engine that we built. It's really at the core of everything we do. That will basically collects all the information globally that we could ever want. And that is all we use to react on, is all we use to drive our system. Mimia is what we call our placement engine. Then, of course, there's a lot of command line tooling that we need to build. Log aggregation. Log aggregation is one of the few things that's actually built on standard tooling, like FileBeat, Kafka, Elk. Then there's security and host level access. So particularly with all the compliance stuff, we kind of need to make sure that only people who need to have access, and somehow manage that. We have this Git-based configuration service, incremental rollouts, and this actually is an interesting thing, because you kind of want to, when you upgrade your database, you kind of want it to work. And I wouldn't be surprised if many of you probably have some kind of staging environment where you try new versions, it kind of works, so let's put it out there and see what happens. And you do some kind of migration, and then maybe not, does it work? It's all typically a manual process. There's no monitoring. Is there a rollback even? Maybe. Typically not. So built into this is also a facility through the UI, you can go in and say, I now want to upgrade this particular instance or all our clusters to a new version of Cassandra or MySQL, and that will actually go through a rolling upgrade process where you can kind of continuously monitor. You can also upgrade by tiers. So we have like a tiering system where we can upgrade all our test instances first, and then all our internal instances, and then kind of the real-life traffic instances last, and verify that everything works. And if you want to do the whole automation part, you probably also need some kind of reliable execution of your changes. So workflow engine, and you also need some kind of way of analyzing what is the current state and what should we currently be doing. Right, so that is more or less what I have. I will be happy to answer questions. As I said before, just a small caveat, I can answer any technical question, almost, but questions about Uber as a whole is kind of off limits for me. Yes?
So you mentioned that you have, that you're switching to array and all that, but obviously earlier on when you showed how you've structured things, you want to avoid having to move data. So what steps do you take? Say you have a host app, what do you do? I'm guessing it's replicated, but if you could give more information.
If you have a what?
If you have a host outage.
Yes, a host outage.
Yeah.
Okay, so how do we react to host outages? Well, particularly around like not moving data around, right? So first of all, you'll notice that we don't have a distributed like block storage. We just have like, we place a node on a host, and that node gets access to the host like more or less raw device. And that's kind of, it's half a conscious decision, and also we just don't have block storage. But even if we had, typically block storage comes with like replication in itself and safety, but we already have all the safety running in Cassandra and schemaless and whatnot. So there's no reason for us to replicate even more. So that doesn't really answer your question, but it might, it's related at least. But we do try to not move stuff around. Of course, if you have a host failure, you kind of lost the data. So now you have to kind of recreate it from somewhere else. And that is really storage engine specific, how that works. Cassandra, for example, will just stream it from other nodes. Elasticsearch will do the same. MySQL, you basically just take a snapshot of one of the other nodes and transfer that over using something like extra backup. Yeah. Any other questions? Everybody's baffled by right? If nothing else, oh, there was one. I'll have to come closer because I cannot hear.
Would you recommend to use databases on Docker for small-scale operations, so like I have microservices and that?
So the question was, would I recommend using Docker for like small-scale operations if you don't have all this large-scale stuff? So Docker definitely has the advantage that you get this isolation and the standard, get a standard build, you get the isolation part, might or might not be necessary, but you run different versions, you can run them locally, you can use the exact same image on your laptop as you use in production. So I think it makes a lot of sense. Plus you can have the exact same host image, like your base host image can be the exact same, you just need to install Docker daemon and you're good to go. You can use it for stateful or stateless, all fine. So personally I think it's a good idea. Just be aware it's not free. That you kind of have to build other tooling. Docker itself won't solve a lot of problems for you. It's all the tooling around it that will do that. Hmm? So is Odin only an abstraction for managing databases? Yes, it basically is. It is.
So it's up to every backend to consume either MySQL directly or Cassandra or whatever?
Yes. So this is purely a management thing. If you are a service who wants to use MySQL or Cassandra, you will just get MySQL or Cassandra. Odin will expose to you how to connect to it, and that's basically it. But you will basically get like raw data store access. No, there's no abstraction on top of the storage engines. Well, that's not completely true, but you can get access. If nothing else, then I am around if you want to ask more questions. Otherwise, thank you very much.